Okay, now omega is rotational velocity. You basically think of it as the speed at which the thing is rotating. It's actually velocity, which could be positive or negative. We'll worry about that distinction a little bit later. But it's how fast the thing is rotating. And what's happening to how fast it's rotating? Well, its rotational speed, or rotational velocity, in this case, is obviously decreasing. And if the graph really is a straight line, if the trend really is a straight line, then it looks like omega, the angular velocity, is changing at a constant rate. Okay, so straight line omega decreases at a constant rate. Okay? And what is that rate? Now this is a pre-calculus concept. You actually get rates in algebra courses, but it's, you know, pretty well formally established in a pre-calculus course, or it should be. And then in a calculus course, you relate the rate to the derivative, and you relate the slope to the derivative, okay? Because the rate can be identified with the slope of the graph. Okay, so slope is rate, or the rate is the slope. So what's the slope of this graph? Well, slope is rise divided by run. Everybody hopefully knows that. If you've had a calculus course, that's been second nature for years, hopefully. Some calculus courses are just taught, you know, to do a bunch of symbol manipulation with no meaning. That's not really a complete calculus course, I'm afraid. Okay, so anyhow, don't know where you had your calculus, but you have to understand that the rate is identified with slope, and you have to understand what that means. I'll probably discuss that a little bit, especially if people seem to be a little confused about it when we actually get to meet, which will be Friday for the lab session. Rate is a slope. Okay, what's the slope of this graph? Rise divided by run. Well, if we take the intercepts, because conveniently this graph goes through the intercepts at widely spaced positions, it looks like that's about 250 on the x-axis, and it looks like that's about 105 on the y-axis. So the rise would be from 105 down to 0. That would be a rise of negative 105. And negative 105 what? Negative 105, it's degrees per second. I wrote radians because, of course, we do almost all our mathematics in radians, except for triangle trigonometry, functional trigonometry. And you know from calculus that you just can't do calculus. You can, but you don't want to do calculus with angles and degrees. So still, in order to do these calculations, not get a bunch of fractions, the omega calculations, I chose to use degrees per second. Okay? So the rise is negative 105 degrees per second. The run, well, from here, t is 0. And you go over to here, t is 250, the run is 250. 250 seconds. So the slope equals negative 105 degrees per second divided by 250 seconds, which is approximately negative 0.4. I don't have room there to write the units, I'll have to write them below. What are the units? What do you get if you divide degrees per second by seconds? Well, you get degrees over seconds squared. That's degrees per second squared. That's, you can see it as degrees per second, and that has a meaning. It means every second on the average, your angular velocity changes by negative 0.4 degrees per second. Negative 0.4 degrees per second, okay? Change in velocity per second. Okay, so there's our result. Okay, so that's kind of neat. Now, what are we going to do with this curve graph? Well, what we're going to do with this curve graph, and from calculus you can easily establish, and we'll do that, that if this is actually linear, and we haven't proven that it is, we just got kind of an indication, just looking at these, it looks like it's a straight line. Okay? And theoretically it should be, except for glitches from wind resistance and stuff. So if this is linear, it turns out that since this is the derivative of this, that this has to be quadratic, because the antiderivative of a linear function is a quadratic function. And we'll talk a little bit more about that idea, but if you've had a calculus course and understood what was going on, you would know this, okay? And, another way of saying that is the derivative of a quadratic function is a linear function. And we'll probably, again, maybe discuss that in class a little bit to make sure everybody sort of understands it. Okay, so we think this should be a quadratic function. That's actually what physics predicts, and we'll see why and how before too long. So what we're going to do here, we're going to pick, I think the instruction says pick 4 points. I forget exactly how we said we'd do that. We're not going to start here, but we're going to start over here someplace and then do 4 equally spaced points where the last point is pretty close to the end. So there's 2 points, so let's put one here and one here, and let's estimate the coordinates. Now, I didn't do a hugely accurate job with this graph, but of course we'll ask you to do one. Okay, so this point seems to be, I'm just going to write down the numbers, 60, 21. And this one appears to be, what? 60, 70, 80, 88, 35, and that should have been 21 pi. 88 and 35 pi. This one appears to be about 150. And that looks like, what, 47 pi. And this one appears to be 230. And maybe 53 pi. Now what we're going to do in the instruction you're going to have is take these 3 points and plug them in to the form that we expect for a quadratic function, where theta is a quadratic function of time. Oh man, don't have a clean board there. Let's see, we've got some over here. Okay, well, I'm going to stop this because I want to set up the boards a little differently. And we have this much. So this is what you're going to get off of the graphs. Now we're going to use that to find theta as a function of time. And then we're going to check to see if in some sense the derivative of the function we get here is a linear function that we get here. Now we do have a little bit of a problem there, that theta here is measured in radians and up here we're in degrees per second. Got to do a little conversion on that.